Good morning. So today we will continue with aberrations. We looked in yesterday's class at chromatic aberration, and we ended the class by looking at how we could correct it. So just to refresh your memory, we said the idea is you want to correct chromatic aberration for at least 2 wavelengths. So you're not going to use a single lens, because if you use a single lens, you have a single material. And since chromatic aberration is caused by the material we use, if we can somehow use 2 materials, can we put 2 lenses, each of a different material, together and somehow combat the chromatic aberration? So we started this derivation yesterday, and in doing so, we also arrived at a parameter that is defined for every optical material called the V number, and that basically tells you how dispersive that material is. Now, up till now in all your classes, lab classes, you've been using BK7 as a glass. Now you should understand why you've been using BK7. It turns out BK7 is a crown glass, and we also calculated its V number, and it was around 64, right? I think it was 64.5 or something. So this is on the higher side, and a higher V number means it is a lower dispersive glass. Okay, so we use BK7 because it has lower dispersion. And typically, if you see that, it's usually denoted as VD. If VD is greater than 50, we call that a low dispersion glass. Okay. So there are many different glasses. They depend on what are the chemicals that have been used to make the glass. And the crown glasses tend to be lower dispersive glasses. They have higher V numbers. We also have flint glasses, and they will have slightly higher dispersion. Now, it's important for us to use a combination of materials, and our derivation showed us that if we have 2 lenses, and if the combination of the focal lengths and the V numbers of these materials gives us, and I'll just write it again, F1y V1 plus F2y V2 equal to 0. If this is satisfied for 2 lenses in contact, then you can eliminate the chromatic aberration for 2 wavelengths, red and blue. Now note that you have written this equation in terms of the focal length of each of those lenses, but it is the focal length at a middle wavelength, a wavelength that lies in the middle of the visible range. So given that this is the focal length, and let's say this is at yellow, so this is the focal length for the lens 1 at yellow, this is a focal length for lens 2 at yellow. These are the V numbers of the materials used for each of these lenses. If this equation is satisfied, you would have corrected for chromatic aberration for red and blue. Okay. Now, the only way this equation can be satisfied if one of these terms somehow goes to 0, and we saw that the V number for optical materials is never going to go negative, right? Because N of blue is always going to be higher than the refractive index of red light. Therefore, the only way this equation can be satisfied is if one of the focal lengths is negative, and therefore that gives you this idea, you combine a convex and a concave lens. And this is an idea we are going to use repeatedly even when you do correction of other aberrations. Okay. Okay. So in this figure below, you can see there's a combination of 2 lenses, a convex and a concave. And here, what is schematically depicted is you have light coming in that is a combination of all the wavelengths, and because of the selecting the convex and concave such that it satisfies the equation that we just saw, the red and blue are coming to focus at the same point, whereas the yellow is still not focused at the same point. So this is an important point to get across. when we say we are doing aberration correction, we are never or very rarely able to completely eliminate the aberration. Here, it's not that the chromatic aberration has become zero, but if we had just had a convex lens, then we know that the light would have come to focus somewhere here, right? If we had only a convex lens, and then your spread of chromatic aberration would have been over this distance. Because you have combined two different lenses, so you have taken a convex lens, you have taken a concave lens. Not only that, they have different materials. So this has V number V1, this is V2. This combination has corrected for red and blue so that red and blue get focused over here, but the yellow still gets focused over here. However, that means your chromatic aberration now is spread over this distance, much less than without the correction. Okay, so this curve over here shows you. So now we go a step further. We normally in optics, we don't even label the axis. Here we don't even draw the axis. You only draw the y-axis, okay? And the y-axis is, I have labeled it here so that it's clear to you, but you might not see this labeled. The y-axis is wavelength and the x-axis is focal distance, okay? So as you go from blue to red, up the y-axis, you can see here, this is what each wavelength is focusing at. And the fact that this curve actually bends and comes around like this, so that both this point and this point have the same focal distance. That means, in other words, this wavelength and this wavelength have the same focal distance. So this is blue and this is red. That means those two have been corrected. But you can see that the wavelengths over here, and this would be like the yellow or the green wavelengths, right? These wavelengths still have that much difference. They are coming to focus at a point different from where the red and blue wavelengths are coming to focus. And this distance is called the secondary spectrum. It's like the uncorrected or the leftover spectrum. Okay, so this is one way of looking at the aberration curve for a system where some amount of aberration correction has been done. So always remember that when we say we optimize to eliminate an aberration, yes, you could move the stop to the natural stop position, coma is 0 there, so you've actually eliminated coma. But not all aberrations can be completely eliminated. At best, you eliminate them for under certain conditions, and I'll explain what I mean in some detail over the next few slides. But you can get a sense of that in chromatic aberration. When we do correction, we are actually saying we are correcting, what you end up doing is actually correcting for some wavelengths, not all the wavelengths. Okay. We won't cover this in this class, but everything that we have been doing in this course has been related to refractive optics. So we've been talking about taking optical dielectric materials, usually glass. You could also have plastics, but usually we've been thinking of glass, and saying if you vary the shape, you can make a lens which has a certain behavior. You can also have diffractive optics. We'll talk a little bit about diffraction later on in the course. But I can have a lens that is a diffractive lens. And the interesting thing to note there is, I said the V number when I take an optical material can never be negative. And so the corrections that we had to do had to be done by introducing a lens with the opposite sign. And that's why we took convex concave. Diffractive optics works on a completely different principle and will have a dispersion opposite in nature to that of refractive optics. So if we say the V number here is always positive, I can consider this to be negative. And so I can take refractive elements and maybe onto this put a diffractive or add a diffractive element, and because this has a negative dispersion, I can use this combination and correct for chromatic aberration. Okay, so that is also possible. I just wanted to show you this graph because I wanted you to get the idea of just how many different types of glasses there are. We've just been using BK7 because it's a standard crown glass that's used in a lot of optics. It has low dispersion, a higher V number, and that's why it's a relatively safe glass to pick. But you can see that every red spot on this graph is a different glass type. Right? And this is only the glass types that are used in the visible range. We haven't even looked at what happens when we move into the ultraviolet, what happens when we move into the infrared or mid-infrared or deep infrared and so on, right? These are only the glass types that we usually use in the visible range, and you can see there's such a huge variety of glass types. Why would you pick one glass type over another? Well, one thing you now know is you would look at the Abbe number and you would look at the dispersion and pick. And when you're combining convex and concave to reduce chromatic aberration, you would take a convex crown, that is a convex with a low dispersion, plus a concave with a high dispersion, so a flint glass, and combine those two to do that cancellation. So that might be one reason why you might pick something which has higher dispersion. But you could go to all of these glass types and understand there are many different reasons why you would pick one over the other. And we are not looking at those details in this course, but glass is a very strong material. But even there you quantify the strength of the material. So how easy it is to scratch. So if you apply pressure with a sharp object and you apply that same pressure over many different glasses, the kind of scratch you get, the depth of the scratch you get will be different. And clearly you want, for many applications, you want the material to be scratch resistant. So you may choose one glass over another because of its physical properties. You may choose one glass over another because of its chemical properties. Where is it being used? What temperature is it going to see? You don't want it to change shape or refractive index when it is in a higher temperature environment. So you will look at its physical properties, its chemical properties, its optical properties. We've talked about refractive index. All of these glasses have different refractive indices, and you know now why refractive index is so important. But what is not mentioned here is transmission of these glasses. When we say glass, we tend to think it's 100% transmissive, right? And if you remember your Maxwell's equations, you know that every time there's a surface, there's a reflection. So depending on the refractive index difference, some light is going to get reflected, but you want that to be as minimum as possible. There are things you can do to reduce the reflection. Let's say you do all of that, you still want the glass to be transmissive and not absorbing light. So you have to look at, do these glasses absorb? So all of those will be parameters you will take into account when you're actually choosing a glass type. And some glasses will absorb in some regions of the visible more than in other regions, and that might also be a reason why you pick one glass type over another. But this just shows you snapshot of the wide variety of glass types that fit over there, right? And you can see our BK7 is sitting over here, Abbe number greater than 60. Okay? Okay. So as I said, we do combinations now, and you understand that the combinations would be negative and positive focal length low dispersion plus high dispersion material. And every correction I do now, if I just take two lenses, you have already seen you can correct for blue and red light. Right? But that may not be good enough for you. You may want to correct for more wavelengths. Then I need to put in more elements. Right? And you can see here you have different combinations. Now, you might ask, if two elements does the job, why go for more and more? Because the question is, two elements doesn't always do the job. Why don't I always go for more elements then? Because of course the design complexity increases. You have that many more variables to optimize, and these are not problems where if I give each of you an optimization problem, the same optimization problem, I'm not going to get one solution, and not because you make mistakes. Okay, assuming you all did everything correctly, if there are 18 of you in the room, I will get 18 different solutions. Right? You're working in this huge space, and you could end up anywhere in that space. It's a very difficult problem to solve. Right? So you want to minimize the number of elements you're working with. You want to minimize the number of variables you're working with. And every time you put in another element, then it's the material of that element, the focal length of that element, the shape of that element, the location of that element. All of these parameters, that is just for one element added. And now I do that, I have to add all of these for every element added. So you can imagine very quickly it can become an extremely complicated problem to solve. So it's a trade-off. How accurate do you need your system to be? How much do you need the aberration to be corrected? To how many elements are you willing to have in your system? It also becomes bigger, more cumbersome. To how much computational effort are you willing or able to put into it? So all of that, and then the glasses that you choose, if I say I have to have very different glasses, they can start becoming expensive. So the cost. So all of this together will decide how many elements you need, and then those are the ones you will use and optimize to get to a system with minimum aberration. Okay, but you can see here, just the first example had two elements. The top one has 4 and the lower one has 3, and you could choose any of these kinds of configurations, because each of them will give you some advantages, while it may in some other sense give you a disadvantage, because it may make the system more complicated or harder to calculate or optimize. Okay, I just want to now kind of do a summary, because we've looked at, in fact, we've come almost to the end of our geometric optics section of this entire course. We will move on to waves after this. So if I look at what we've been doing over the last few weeks, we've been looking at aberrations. We went through what are the different monochromatic aberrations, what causes them, where they're predominant, how do we quantify them. And then we have also looked at the chromatic aberrations. And with the chromatic, we did actually a slightly detailed look at how we correct for them. And I want to extend that idea now to correction in general. Okay, so you had this idea already with the chromatic aberration, that you correct the simplest correction was with 2 lenses, and this gave you 2 wavelengths corrected. Now, one way of looking at that was the curve we had on the previous slide, where we said it's corrected something like this. So this was lambda, and this was red light, this was blue light, this was focal distance. So even though we said there is aberration correction, the correction was only for 2 wavelengths. I could also look at this in a different way. So I again do focal distance, but this could then be ray height, not wavelength. Okay. And again over here, it could be that it's something like this. So you have to be very careful with the word aberration correction, because up till now I said, okay, you can correct for two wavelengths, but it may be that you've corrected for two wavelengths and those two wavelengths are best corrected for only one set of rays. Even those two wavelengths are not perfectly corrected for all the rays incident on the lens. And that's what the second graph is telling you. This is ray height. So these are the rays on the axis. So the rays on the axis are corrected. There's zero error, or they come to this focal position. As you move up the lens, so you have a lens and you have rays that are incident different places on the lens. These rays we consider irrespective of lambda getting focused correctly. I'm drawing a single lens, I'm talking about a corrected system. Okay. As you move up, these rays, just because of their location on this corrected system, are not being corrected. And then again the rays over here, so you have correction here and you have correction here. So you have to look at all these curves to understand what the actual correction is. It could be that you correct for different wavelengths, but you correct for those wavelengths for a set of rays, one annulus or certain zones of the lens. The rays incident on those zones are corrected, the other rays are not. Right? So this is nothing but your longitudinal error kind of, right? So looking at this tells me, this curve tells me two wavelengths are corrected. This curve tells me the paraxial rays and the marginal rays are corrected. There's still an error over here. Okay. So this point I really want to stress. Whenever you do correction, you are achieving correction possibly for some wavelengths, possibly for some rays. And when I say some rays, I mean only some annular zones, rays incident on those annular zones of the lens are corrected and not the others. And that's why it's important to go and look at these transverse and longitudinal. These are not transverse, these are longitudinal aberration graphs or the wavelength aberration graphs, because they tell you how well the correction is. Right? If you had no correction, this graph here, so this graph here, it would look like this. Zero error for the paraxial ray. As you go up with ray height, the further and further rays experience more and more correction. So what the correction is doing, the addition of that second element, it is changing the curvature of this. So you do this and then it bends like this. So there's a region it's still unable to correct for, but it corrects over here and it retains the minimum part of it. So that's how you think of the correction. And you will see these kind of curves in all the kinds of aberration correction you do. So I could also look at this is also a typical graph that you might get. So I have that's the blue line. So this is ray height. Okay, I'm showing you a correction of aberration, chromatic aberration. Might have something like this, right? And okay. So you can see this point here, red and blue are corrected. They have the same focal length. So for those height rays, those two wavelengths have the same focal length, but for any other set of rays falling on the lens, they have different focal lengths, right? So you need to look at all these aspects to actually judge the level of correction that has been achieved in a system. And this is why you might use more than just two lenses. These graphs are typical of what you would get of a what is called an achromatic doublet, because you've used two lenses for the correction. And you can see that while you achieve correction for two wavelengths for one annular zone of the lens, you haven't achieved correction anywhere else or for any other wavelength, and that may not at all be acceptable for your application. In that case, you know that a doublet isn't going to work for you. You're going to have to add more lenses into the system with their spacers and use all of that to achieve much better correction than this. Okay?